Okay, let's look at a couple problems here. What is a spontaneous reaction that occurs when a copper half cell is combined with a silver half cell? First off, go back to the electromotive series and get the half reactions. The half reactions look like this. Copper half reaction, the standard reduction potential is 0.337. And for the silver half reaction, the standard reduction potential is 0.800 volts. Now, in order to be spontaneous, the standard cell potential has to be positive. So when I add the anode to the cathode, I need a positive standard cell potential. I'm going to have to flip one of these half reactions. The one I'm going to flip is this one up here with the copper. When I flip it, the standard reduction potential becomes negative 0.337 volts. To the silver, I'm going to have to multiply by 2 because I need the electrons to cancel. However, I did multiply the equation by 2, but the standard reduction potential does not change. It is still 0.800 volts. The only reason I multiplied by 2 was to cancel out the electrons, because overall equation cannot have electrons. But you do not change the standard reduction potential. So my overall equation looks like this. And the standard cell potential, when I add the anode to the cathode, comes out to positive 0.463 volts. So it is spontaneous because the standard cell potential is positive. So let's look at this one here. We want to know what's going to oxidize what. Again, we're going to pull the half reactions from the electromotive series. Here's my 10 half reaction. The standard reduction potential is 0.15. And then for nitrate, we have this half reaction. And the standard reduction potential is 0.96 volts. Again, we want a spontaneous reaction, which means the standard cell potential is positive. I'm going to have to flip one of these equations around, and then what I'm going to flip is the 10. And so the standard reduction potential becomes negative 0.15 volts. The nitrate, keep the same. So the standard reduction potential is still 0.96 volts. However, in order to cancel out the electrons, we're going to have to multiply these equations by 3 and 2 respectively to get the overall equation. So the overall equation looks like this. but I'm not going to multiply the reduction potentials by 3 and 2. I'm simply going to add those reduction potentials together, so the overall standard cell potential is positive 0.81 volts. So it is spontaneous because the standard cell potential is positive, and in this case, nitrate ions oxidize the tin ions spontaneously. The Nernst equation was derived to calculate electrode potentials and cell potentials when we're not at standard state values. The Nernst equation looks like this. The electrode potential equals the standard electrode potential minus 2.303 RT over NF log of Q. There are quite a bit of variables with the Nernst equation, but we can simplify the Nernst equation. At 25 degrees Celsius or 298 Kelvin, the Nernst equation looks like this. A little less daunting. We just got rid of some of those variables if we are indeed at 298 Kelvin. So let's look at this example that involves the Nernst equation. We're calculating the reduction potential for the iron electrode, where the Fe2 plus concentration is 5 times that of Fe3 plus. If you go back to the electromotive series, we can get the half reaction that looks like this. And the standard cell potential is 0.771 volts. I want to know the reduction potential, E. So I'm going to use the Nernst equation. Q is products divided by reactants. It would be Fe2 plus over Fe3 plus, based on this equation right here. So plug in our values. Standard cell potential is 0.771 volts minus 0.0592 over N. N is the number of moles of electrons. I'm only transferring 1 mole of electrons times the log of Q. Well, Fe2 plus is 5 times that of Fe3 plus. So that'd be the log of 5. And so the reduction potential under non-standard conditions is 0.730 volts.